All right, good morning, ladies and gentlemen. Hope you guys are doing well. Welcome back to another video with Mr. Kenton for HL Chemistry. We're moving through topic 3, which is periodic trends, essentially, and now we're moving into looking at some more specific things as it pertains to the D block elements, and specifically that first row. So we're going to be looking at some of the transition metals here with this particular video. So glad you guys could join me. Let's go ahead and just get started here. Now, this is going to be kind of the big idea that we're looking at within this particular section or this particular topic within HL chemistry, is that the transition elements have characteristic properties and that these properties are related to them having incomplete D subshells, right? For most of them, right? Obviously, there are going to be some that have a complete D subshell, but we'll work through that as we get through it. And we're also going to be looking for trends and discrepancies within the transition, because what we can find is that transition elements, like the other elements on the periodic table, follow certain patterns of behavior. Now, we do need to note that zinc, chromium, and copper, they are going to deviate from those patterns a little bit more, and so we would say that those would be anomalies in the first row of the D block on the periodic table. Okay. Now, again, just keeping the perspective of how does chemistry apply to not just simply the sciences, but how does chemistry influence other areas of our life? We think about the transition metals and what makes their properties and what make them international commodities. We think about it. Mining for some of these metals is actually a major factor in the economies of some countries. So certainly chemistry and our understanding of these compounds can have an economic impact in terms of how countries function. So chemistry is cross-cutting in that regard, that it's able to impact economics and historical aspects as well, right? And then TOK, thinking of our theory of knowledge, in the past, the medical symbols for female and male, they originate from the alchemical symbols for copper and iron. And so something for us to consider, what role has the pseudoscience of alchemy played in the development of modern science? Now, I'll be totally honest, I haven't heavily investigated alchemy all that much, but it is interesting that a lot of foundational things, like a lot of chemistry, did start out from just kind of understanding that people thought alchemy was what was going on. People were changing things from one substance to another. So it's just an important thing to consider as we're moving forward. Now, when we look at what we're going to be taking a look at first, we want to look at how the transition elements have variable oxidation states, form complex ions with ligands, they have colored compounds, they have catalytic properties and magnetic properties. Hopefully these terms are not new to you guys, but we're going to be looking at those things. But before we can dive into that, we need to get just kind of a good overarching view of what are we going to be looking at with the D block elements in terms of their physical and chemical properties first and foremost, before we dive into some of those things. So with that being said, we think about the elements that are in the D block, and most people think of those as like, okay, iron and copper, right? And when you look at the first row of the D block, those are elements that you find there, iron and copper, right? Now, when we think about specifically the first row of the D block, the 10 elements of the first row of the D block, those elements, surprisingly, have similar chemical and physical properties, right? And the reason why that's surprising is because if you look at the general trend on the periodic table, as you move across periods, we see that the chemical properties and the physical properties of those elements change pretty drastically from going from group 1 over to group 18. But within the transition metals, within the D block, the variation is going to be a little bit less, and we're going to dive into why that's the case, right? So these 10 elements show a lull in the periodic pattern that we've seen in the S and P block elements, and it has to do with the fact that we've got this D block or these D subshells that are being occupied in these particular elements, right? Now, the similarity in properties of the first row D block elements is illustrated by the small range in atomic radii. Now, the reason why the atomic radii is a lot smaller, there's not as much variation, is because each of the elements on the D block, they're adding one new electron to a D sublevel, which is roughly the same in energy, is close to, in energy to the S block. And so when you keep adding those electrons, what happens is there's a small decrease in atomic radii due to the fact that the outer 4s electrons experience only a small increase in nuclear charge, right? We talked about how nuclear charge is essentially the pull of the nucleus on the valence electrons, right? And so as we're moving from left to right across the D block, the increase in nuclear charge is much smaller than we would anticipate. And that has to do with the shielding due to those D block electrons that are being added, that are going to be filling in kind of those core electrons of the atom. Right, so the expected increase in nuclear charge that we would anticipate due to each proton being added is offset by the addition of those electrons to the inner 3D sublevel. And so looking at that as well, the small increase in radii also accounts for the small increase in first ionization energies across the first transition elements, right? So just like atomic radius is changing very little as we move across, same thing is happening with first ionization energy. And it has to do with the fact that the increase in nuclear charge is being offset by the addition of electrons into that 3D sublevel. All right, and so if you just take a look here, I'm not going to go over everything that's here, but I've given you guys the elements that are in that D block, given you kind of their core electrons, and then shown you their electron configurations, right? And the only thing that I would draw your attention to is don't forget that chromium and copper are slightly different. Remember, chromium 4s1 3d5, and then copper 4s1 3d10, because they prefer, like, it's energetically favorable to have those half-filled and completely filled d orbitals, as opposed to having a completely filled s orbital, right? And again, the thing that we're noticing, we're just increasing the number of d electrons as we move across. Now let's take a look at some of the properties that are like characteristic of these transition elements. Now, starting with physical properties. So these are things that we observe about them. The transition metals, specifically that first row D block, they have high electrical and thermal conductivity. They have relatively high melting points. They're malleable. That means they're easily made and molded into different shapes. They have high tensile strength. That means they can hold large loads without breaking. So from like a material science perspective, using the transition metals in manufacturing and things like that, really valuable because they're really sturdy. They're sturdy substances. They're ductile. They're easily drawn into wires. You think about how those applications of like copper wire that's used in electrical components, talking about wires and things like that. Copper is very common because it can be easily drawn into a wire. Well, all of those physical properties really go back to kind of the presence of these d orbitals and these d subshells, right? And so these properties can be explained by strong metallic bonding within those elements, right? And this is because the 3d and 4s electrons are close in energy. And so within metals, the 3d and 4s electrons are going to be a part of the delocalized sea of electrons, which hold the metal lattice structures together, right? So you think about metallic bonding. We talked about how the electrons they're not confined to one particular space. And so since they have the freedom to move, the 4s and 3d electrons are more mobile than in other elements. And so as a result, we get to see those properties like electrical and thermal conductivity, malleability, tensile strength, and ductility within our D block transition elements, right? Now, chemical properties, we know that chemical properties are mostly related to the valence electrons of an element, right? And so it's important to recognize that with the exception of zinc on that first row, the 3D elements are transition metals. And so when we say transition metals, we're talking about how these elements can form compounds with more than one oxidation number, right? So remember, zinc always forms a 2+ charge. It never forms anything else other than that. Whereas the other elements that are on the D block can form multiple charges within a compound. Now, that means the rest of them, they form a variety of complex ions as well, which we'll get into a little bit more later. They can form colored compounds. So like if you think about in the flame test lab, or even when you're making solutions, that's what explains why like copper solutions are very blue. You could look at other compounds, like I think of cobalt, forms like a pinkish color, right? So the reason for that has to do with the fact that these transition elements can form various different oxidation states, and so you get these colored compounds. Now, the other thing with your transition elements, they can serve as catalysts when they're either elements or if they're in compounds. And if you recall, we'll look at catalysts a little bit. Remember, just a catalyst is something that can speed up a chemical reaction. All right, and then for your transition elements, these elements on the first D block, first D row, they have magnetic properties. Some of it might be due to ferromagnetism, but then some of it might also be due to paramagnetism versus dimagnetism. All right, last thing that I want us to look at through kind of this particular video is looking at our transition metals as catalysts, right? And so if you think back to your understanding of kinetics, remember, kinetics looks at the study of reaction rates. And so a catalyst is simply a substance which is going to alter the rate of a reaction. So it's going to speed it up by providing an alternative reaction pathway with a lower activation energy, right? So remember, all reactions, they have to overcome some initial hill in order for them to get kick-started, right? Some of those reactions are have relatively low activation energies. Some of them are really high. Well, what a catalyst does is it provides an alternate reaction pathway, and typically one way it does that is by lowering that activation energy, the energy required to kickstart the reaction. Now, when you start to look at catalysts as a whole, they're very essential in the chemical industry because what they can do is they can allow a particular chemical process to proceed in a way in which it's going to be economical. It's not going to be something that's overly time consuming. It's not going to be super expensive because the catalyst is going to speed up that particular process, right? And so the neat thing is our D block, first row D block elements can serve as catalysts in many processes. Now, there are two different types of catalysts. You can have a heterogeneous catalyst, which simply means that the catalyst is going to be in a different state of matter than the reactants. Okay, so for example, the reactants may be gases and the catalyst could be a solid. This is very common like in catalytic converters. What you have is you have gases that are being produced from your car, and then there's a transition metal catalyst that's a solid, and what it's able to is it's able to bind to those reactants to cause the reaction to speed up. And so the ability of our transition elements to use the 3d and 4s electrons to form weak bonds to small reactant molecules makes them pretty effective as heterogeneous catalysts. Because what they can do is they can provide a surface for the reactant molecules to come together with the correct orientation. So think of it as the catalyst serves as kind of a bonding site for the reactants to meet up on. They react, and then they form their new compounds, and then they come off. And so the new reactant molecules can come on, get in the proper orientation, bond, and then remove, right? So that's how transition metals function as heterogeneous catalysts. Now, the other type of catalyst is homogeneous catalysts. And so homogeneous catalysts are going to be catalysts that are used, but they're going to have the same state of matter as the reactants that are reacting. Okay, and this is going to be most common in reactions that are involving solutions. So the ability of transition metals to show variable oxidation states allows them to be very effective homogeneous catalysts, specifically aqueous solutions, specifically in redox reactions, right? So in reactions where there's a transfer of electrons that is taking place. Now we can also think about it from this perspective. Homogeneous catalysts are really important from a biological perspective. A lot of ways in which the human body functions has to do with the fact that there are homogeneous catalysts that help speed up biological processes within our body to help the body run and function properly. Okay. All right. So that's going to do it for this particular video. I wanted to get through kind of the general properties of the transition elements, the first row, the 3D block, and then talking about their catalytic properties as either heterogeneous or homogeneous catalysts. So if you guys do have any questions, please don't hesitate to ask, bring them to class. I'd be more than happy to take a look at them. So thank you guys for joining me. Appreciate you guys and look forward to seeing you guys again soon. Take care.